We have discussed cables as woven structural elements that can only support tensile forces, but cables are also used in conjunction with another structural element, the pulley. A pulley is a wheel with a grooved rim around which a cable or belt passes, and is used in one of several functions. It is used to either 1. Redirect the cable tension, 2. Reduce and redistribute the tension among multiple parallel cables, or 3. Transmit torque. This last application is found, for example, in a traditional internal combustion engine where the crankshaft drives a pulley around which is wrapped a serpentine belt that in turn drives other system components. Transmission of torque through a belt pulley system requires the pulley to grab the belt through friction, and this leads to a continuously varying tension within the belt along the contact surface with the pulley. In the present case, it's assumed that we're applying a clockwise torque through this crankshaft. The large pulley is grabbing the belt, and in doing so, there is a larger tension on this side than there is on this side, with continuous variation all along this contact surface. Assuming this small pulley here is frictionless, there's a uniform tension, TABC, all along this left-hand side. So the tension acting on this small pulley up here is also TABC. The tension on the right-hand side here is also TAC. And this difference in tensions on either side of the small pulley is used to apply a torque which is resisted by some kind of torsional load in the background here. Maybe it's driving a motor or a pump or some other device. As with the large pulley, there is also a continuous variation of tension along this contact surface. We will eventually get to this application, but not until much later in the course after we've had a chance to discuss friction, and in particular belt friction. For now, we will focus on cables and pulleys in the first two applications, redirection and reduction and redistribution of tension. Even though a small amount of friction may need to be present so that the cable doesn't slide over the pulley surface, we will assume this friction is negligible. The result of these assumptions is that any continuous cable segment wrapped around one or more pulleys will be assumed to have the same tension. In this example, it doesn't matter that the cable is wrapped around 3 pulleys or that it has this very contorted path around those pulleys. There is the same tension at any location in the belt. The presence of a pulley might seem to complicate free body diagrams, but the situation isn't as complicated as it first appears. In this schematic, we have a cable segment with one end attached to a ceiling, indicated by the cross-hatching, and the other end attached to a shackle. A shackle is a U-shaped metal link, shown in green here, with a shaft shown in blue attached to the ends. The pulley is mounted on the shaft through bearings that we can't see directly, and is free to rotate about that shaft. Isolating the pulley requires a closed surface that passes through the pulley shaft interface at the bearings, and also that cuts through the cables passing on either side of the pulley. To understand what reactions are required at the shaft-pulley interface, we have to ask what degrees of freedom are impeded or prevented by that shaft-bearing interface. The term degree of freedom refers to a translation or a rotation. As part of the treatment of the pulley being frictionless, we also say that its bearings are frictionless, thereby offering no resistance to the pulley's rotation about the shaft. The only degrees of freedom being prevented are translations, as the pulley can't actually be pulled through the shaft. On the basis of this enveloping surface in red on the right, we can draw a free body diagram of the pulley, and from the side in the XY coordinate plane, that free body diagram would look like this. Here we have the pulley, again viewed from the side. We have cables at these locations that we're cutting through as part of the isolation process, and we're assuming that there's no or negligible friction between the cables or belts and the pulley, so we have a uniform tension T on either side. And then at the interface between the pulley and the shaft, because the translational degrees of freedom are prevented, we have reaction forces which we can represent, for instance, as AX and AY. The force components AX and AY represent the forces that develop as we try to pull the pulley through the shaft. There is a more appealing way to represent these forces, and we can see this if we choose a different enveloping surface for the free body diagram, one that encloses the entire shackle shaft pulley assembly and cuts through the upper cable segment as well as the lower cable segments. Here the enveloping surface would look something like this, and the resulting free body diagram would look like this. Now we have a force F in the upper cable segment, and we have the tensions in the lower cable segment, uniform tension T on either side. Note that none of the interacting forces between any of the components of the assembly, the shackle shaft pulley assembly, appear in this free body diagram because those are all interior to the enveloping surface directly above. For this particular free body diagram, it is useful to establish a different coordinate system with one axis being parallel to the upper cable segment. So we'll draw this dashed line, and we will call this direction the tangent direction. I'll give that a unit vector in T subscript, and then orthogonal to that, we will have a unit vector in the normal direction. We'll establish angles between the two tensions and the tangent direction on either side. We'll call this angle theta and this angle phi. We can now write equilibrium equations based on this free body diagram. If we take the sum of the forces in the normal direction and set those equal to 0, you'll notice that we have T sine phi minus T sine theta equals 0, and that tells us that phi is equal to theta. This is an important result for a configuration like this where we've got a single frictionless pulley and a cable that's supporting it through a shackle like this. Because what it tells us is that the line of action of the force in that upper cable segment has to bisect the angle made by the two cable tensions below it. We can now get an expression that relates the upper cable force F to the cable tension T by writing sum of the forces in the tangent direction equal to 0. And taking advantage of the fact that phi is equal to theta, this is simply going to give us F minus 2t cosine theta equals 0, or F equals 2t cosine theta. If we like, we can now disassemble the shackle from the pulley and get an alternative free body diagram from the first one that we showed right here. Equilibrium of the shackle in the tangent directions requires that the net force at the shaft be also equal to F, equal and opposite to F. But since we know that F equals 2t cosine theta, we could alternatively represent that in the following way. We have our force F here, and then we could say that we have tensions T making angle theta on either side. Note that that is equivalent to taking the forces that exist at the pulley and transferring them directly to the bearing of the shackle. For the pulley, separating the shackle from the pulley at the bearing gives us a force F equal and opposite to this force. And then we also have the two cable tensions. But since again we know that F is 2t cosine theta, we could represent the forces at the pulley bearing as equal and opposite to those cable tensions directly. There may be instances when it's convenient to leave the pulley on its bearings, and other instances when it's convenient to remove it. As the figure shows on the left here, the bearing forces exerted on the shackle by the pulley can be represented by shifting the forces carried by the cables to the bearing center. The bearing forces exerted on the pulley by the shackle are equal and opposite to those carried by the cable. If we wish to do so, we could take the bearing forces, resolve them into components in x and y, and then define a net ax and ay as we had in our very first free body diagram. So we could get back to our first free body diagram of a pulley if we so desired. We summarized these results with a brief movie showing an enveloping surface isolating the pulley shackle assembly. We show the two cable forces T and the upper cable segment force F, then separate the shackle from the pulley and show the reaction forces, the bearing forces at A. Instead of an AX and AY, we show the bearing forces as parallel to the cable segments, and they have to be equal and opposite. Perhaps the only thing not shown by this movie is the fact that the upper cable segment bisects the angle subtended by the two belt tensions T, so the angle theta is missing from this movie. We could fix that by annotating these two separate free body diagrams with the angle theta. We now start to look at more complicated examples with more features competing for our attention. As a general rule, look for intersections of interacting members as good candidates for free body diagrams. There may be more than one for each problem. For each free body diagram, we can write two equilibrium equations in 2 dimensions. If the number of equilibrium equations matches the number of unknowns, then we typically have enough information to solve for the unknowns solely on the basis of equilibrium, and the problem is said to be statically determinate. If the number of unknowns exceeds the number of equilibrium equations, this isn't bad or wrong, it just means additional information must be brought to bear in order to solve the problem. Equilibrium alone is not sufficient, and the problem is said to be statically indeterminate.